This will be a short video in which I will look at vector calculus identities. You can think of this in the same way as when you learned trigonometry, you then learned the trigonometrical identities, cosine squared plus sine squared equals 1, and so on. So there are some identities related to the gradient and the divergence of fields. So, for example, let me start by the properties of the divergence. What is the divergence of the addition of two vector fields A and B? Turns out that the divergence is simply equal to the divergence of A plus the divergence of B. Okay, that's very easy. What is the divergence of a vector field which is given as a scalar field phi multiplied by a vector field A? And the answer is that this is equal to the scalar field phi multiplied times the divergence of A plus the vector field A dot product with the gradient of phi. This should remind you to the derivative of a product in some sense, right? You remember that the derivative of a product is the first term times the derivative of the second plus the derivative of the first times the second. And that seems to be what's going on here. So it's the first term times the derivative of the second, but since the second is a vector field, you need to calculate the divergence, plus the second term without derivative times, and you need to do a dot product because this is a vector, times the derivative of the first, which since the first is a scalar field, you have to do the gradient of this scalar field. Okay, this explanation of the analogy to the product rule is very informal. You won't find it in textbooks. It's just a trick I used to remember it. But the correct way would be to actually derive this by applying the definition of the divergence, doing the partial derivatives, and seeing that you can write it in this way. Okay. Next, I can talk about the properties of the curl, and I can do something very similar. What is the curl of the addition of two vector fields, A plus B? So it's equal to the addition of the curls. So that's great. Okay. Now, interestingly, what is the curl of the product between a scalar field phi and a vector field A? So now you might be tempted on following an identical structure to this, but changing the dot with a cross, and you would be almost correct. Let me write it. The only thing where you would be wrong is that this has to be a negative sign. Okay, so that can be proven by calculating the curl of this product and then calculating the right hand side, and you will see that the two things are equal if you substitute the actual derivatives. Okay, so there needs to be a minus sign, a negative sign here. Okay, I guess this negative sign you could get rid of it by placing this in front and this on the other side, because the vector product, the cross product, of course changes sign if you change the order, right? But okay, so those are the properties of the divergence and the curl. Don't worry about remembering this. If you ever need to do this operation or this operation, I would give it to you in the exam. Okay, in the question itself, I would write as a hint, remember the property this or this. I don't ask you to remember this. Now, what I do ask you to remember, because this is extremely important in physics, it appears very often, is some combinations of the curl, the divergence, and the gradient. And that's why I've written here this yellow box, because this is really, really important. This will appear lots of the times. So what if you calculate the curl of the gradient? So the curl of the gradient is nabla cross the gradient of some scalar field phi. If you try to do this calculation, you apply the, so you you write explicitly the derivatives, and then you do the cross product with the new nabla, and what you get is that this is equal to 0, which is very interesting actually. This is 0, and this is related to the fact that the second order partial derivative with crossed variables, so when you do partial of x and then partial of y, that is equal to partial of y and then partial of x. So you will see that if you actually try to prove this, it's relatively simple. You will get subtractions of those terms, and since those terms are equal, the answer will be 0. Next, you can try to calculate the divergence of the curl. Okay, this means you apply nabla dot the cross product of nabla with f. So the divergence of the curl. And if you try to do this, once again, the result is equal to 0. Okay, so this is a very common result in physics, that the curl of a gradient is 0 and the divergence of a curl is 0. Next, there are some other results which I don't consider so important, but anyway, I want to teach them to you. So now I put them outside of the golden box. The divergence of a gradient. So the divergence of a gradient is nabla dot the gradient of a scalar field. And if you develop this, this ends up being equal to the second order partial derivatives added up. Okay, and this is often written, and I use equal sign with 3 lines, meaning that by definition this is equivalent. So this is just meaning that we just write it this way. We write it as nabla squared phi. Okay, and this nabla squared is a new operator which is often called the Laplacian operator. The Laplacian. And you will have seen the Laplacian used in the wave equation. Okay, now to confuse things a little bit, some books and some articles in Wikipedia and so on, they use sometimes a symbol for the Laplacian, which is a triangle but inverted with respect to nabla, which I always find a bit confusing, and I prefer always using the nabla squared notation. But you might find this triangle, and this means the Laplacian operator, which means taking the second order partial derivatives with respect to x, y, and z and adding them all up. Okay? And finally, there is another mathematical identity, which is the curl of the curl. So if you calculate the curl of a vector field f, what do you get? And the answer is this relatively ugly monster, which is the gradient of the divergence minus the Laplacian of f vector. And this Laplacian of f vector, this is called the vector Laplacian, because remember, the Laplacian here is an operation that acts on a scalar and is given by this. But when you see the Laplacian acting on a vector, this is called the vector Laplacian. And the way you calculate it is simply do the Laplacian to each component. And the result is a vector. So let me write it explicitly to make sure there is no confusion here. The vector Laplacian is simply a vector which has the Laplacian of the x component, the Laplacian of the y component, and the Laplacian of the z component. Okay? So that's it. Those are the well-known identities of vector calculus. So see you in the next video.